Hi everyone, thanks so much for coming out, even though it's the middle of summer, and I know that you probably all have places and parties to be at. I'm really excited to talk to you tonight about material science for tomorrow's technologies, particularly why I think it's kind of interesting and what we can do as scientists and engineers to engineer technologies that are better for society and better for the environment. Technology has come a long way in the past 50 years, from computers that were the size of rooms to things that we could fit in our houses, and eventually technologies that we could put in our backpacks. Mobile phones have gone from being things that were a little bit like bricks to technologies that contain the sum of all human knowledge that we can fit inside our pockets. I think it's kind of interesting when you look at this tech evolution, and that if you look at things like solar panels, they haven't actually changed that much. The first solar panel, the first silicon solar cell, was developed at Bell Labs in the 1950s and actually looks remarkably similar to the ones that we have today. I have a special soft spot for mobile phones that you could only play Snake on, but I think that dates me a little bit to say that that was the best time of tech. But we want more of our technology today. We want longer battery lives. We want to be able to use our tech outside without glare interrupting what we're seeing on the image. We want to be able to monitor for different health conditions or detect disease in kind of personal electronic devices. And maybe we want kind of conformable, more attractive green energy solutions. On top of that, we have a massive supply chain issue, particularly in things like semiconductors, and lots of the elements that we need for critical technologies are incredibly rare. This is quite a good graphic I found from a kind of National Energy Technology Center in the States that maps out these elements that are particularly critical for different technologies that we rely on, but at incredibly short supply. We have to mine them, we have to find them, but sometimes even in zones that are particularly dangerous to work in. And these are tech that we need for things beyond things like mobile phones and televisions, things like medical equipment and things like that. Alongside the scarcity of these materials and supply chain issues in fabricating them, we have this kind of evolving, complex geopolitical landscape that makes it harder and harder to get these materials that we rely on. So we have to think differently. We have to think laterally about creating these kind of materials for technologies. At the same time, our kind of love for large language models and AI is driving the increase of these data centers. I'm sure you've heard about the huge power demands that these data centers have. Some of them have the same power demands as cities. They're that big and they're that energy hungry. And that's only predicted to rise in the coming years. Over the next 10 years, it's going to rise by 50%, the power that we consume from these data centers. And if we shift to these phenomenally exciting platforms, things like quantum computing, if we did quantum computing with superconductors, which is one of the various materials platforms proposed for quantum computing, to maintain that quantum state, you have to keep your superconductor in these ridiculously quite beautiful, but also a bit bizarre golden chandeliers. That whole setup, actually, that you can see is all engineered to keep the superconductor as cool as possible to maintain that quantum state, keeping it very close to absolute zero. But that's incredibly energy intensive to do so. Even if you choose photonic quantum computing as your platform, and photons are quite good at encoding quantum information in something like the phase or the polarization of the photon, there you can do all of your quantum computing part at room temperature, but actually to detect those photons, you need to really, really cool down your detectors. So even though some parts of this quantum tech are working at room temperature, you still have this huge challenge in needing to cool those detectors down to almost absolute zero. So kind of the big question I suppose I have is kind of what if we could create materials that didn't cost the earth to do it? And the answer is we can. I think we can solve a lot of this by thinking about chemistry. I'm very excited about all the chemistry coming up at the Royal Institution this year. But by particularly engineering molecules and thinking about the design of molecules, we can come up with new solutions for quantum technologies, optoelectronics, and spintronic technologies. And that's really what I want to try and convince you over the course of tonight. Oh, there's carbon, my favorite element. I gave this talk a really broad title, so I said that it was material science for tomorrow's technologies, and I'm not going to be able to talk about every aspect of material science. As Chris said, I work in a department of materials, and there we focus on lots of different aspects of material science. So some of this is kind of materials for the energy transition, if that's solid oxide fuel cells, or fancy new materials for batteries, or new materials for nuclear reactors. Some of that is incredibly cool materials for healthcare applications, so that could be biomaterials for future bone implants or tissue engineering. It could be nanoparticles for drug delivery. There's a lot of work on sustainable transport, so sustainable aviation and electric vehicle batteries. And actually one of the most wonderful things things about working in a materials department is often to develop these materials. You can't just kind of come up with it in your lab and then one day it translates into a technology. Actually, you have to be able to characterize them. You have to be able to understand them. So we have lots of really fancy microscopes, be they atomic force microscopes or electron microscopes, to be able to do that. So I don't know if I'll be able to get to any of these things in the talk, but if you want to talk about any of them, there'll be fantastic talks at the RI on it. Imperial, where I work, has some great talks on those topics, and I'm always happy to talk about that. But that's a kind of a small caveat. So kind of before I talk about the wonder of materials and this special interest I have, particularly in an aspect of chemistry called chirality, something that you might have noticed is, or maybe not noticed or appreciated as much as I come to do now I work in a materials department, is how much materials underpins our everyday lives, kind of material science and innovations in that. Be they kind of carbon-plated shoes for running faster in marathons, be it graphene that you can implant into tennis rackets to make it lighter weight and stronger, be it thinking really carefully about train tracks so that they can be engineered to not change shape too much when it heats up and we don't affect people's transport too much on hot days like the past few days, or the kind of incredibly clever materials that you have in induction hobs so you can keep cooking in a cool kitchen. All of this has been innovations in material science that's enabled this and made that possible. And I think that's quite a remarkable thing for a subject that most people don't really know about. We've had a lot about materials in the news lately. You can see it's driven a lot of these kind of tariffs and trade wars at the moment. But actually, from a kind of thinking, how do you get into material science, it combines a lot of subjects that you do think about at school. So it combines things like physics and chemistry, biology, maths, economics even, art and design. And it comes together into this kind of beautiful way that you start to think about turning that kind of idea from fundamental science into these technologies that help society through this pathway of engineering. So it's been this really fantastic journey for me. I actually trained in physics. I did an undergrad and a PhD in physics, and then now moved into a materials department where you're thinking, how can I take those concepts that we've worked to understand, these interactions of lighter materials, the transport of electrons through systems, and turn that into a useful technology? So yeah, that's my little primer on why materials is really great. I should also say, it's been this kind of amazing place because I care deeply about kind of art and design. I actually studied art a little bit before I studied physics. And before my jump into undergraduate physics, I spent a year doing art and also living in Italy and learning art. And there you just have these remarkable feats of materials and engineering. I mean, things that when you walk around as a tourist, you don't really appreciate how gigantic they were at the time. But when Brunelleschi built this dome in Florence, I'm not sure who's been there. Maybe you've been there and seen this absolutely ridiculous dome. It's absolutely gigantic. I think it's still the world's largest piece of stone masonry of that size. And it was a huge feat of engineering to do it. He was neither an architect nor an engineer, just had a vision that you could make it possible with ridiculous brickwork, some complex internal structure of these domes. Within that, there's these beautiful frescoes painted by Vasari or started by Vasari. And frescoes, if you know this beautiful period of art, involve painting onto wet plaster. That's kind of a complex nightmare of trying to communicate an intricate design. So you really have these two huge feats of material science and engineering. And then on the doors of the baptistry of this cathedral, you have these beautiful bronze gilded work by Ghiberti. And then another cool part of the Renaissance that connected this kind of art and physics and engineering for me was this beautiful painter called Artemisia Gentileschi, who was friends with Galileo. So if you look closely at her artworks, you can see the projectile of the blood coming from this painting in Judith beheading Holofernes, and it has this perfect parabola because Galileo taught her the maths to make that possible. So you had this kind of incredible overlap between art, science, and engineering that I think we try and squish out now. You know, when you go to school, you learn about these subjects as being kind of discrete and separate from one another. But actually, to be innovative in engineering, you have to be completely creative. To be able to do new parts of physics that people haven't done before, you have to have that kind of creative mindset that you're taught so much in arts and design. And that lends me really well to thinking about a materials degree, but also to thinking we need to radically change education so as many people as possible can create as many beautiful things as this. Okay, sidetracked massively, but kind of back to molecules and why they're so interesting. I told you my favorite element was carbon. Carbon is very interesting. Have we got a little mouse on the screen? Oh, no, it's gone. Carbon's very interesting because it can join up and bond together in lots of different ways. There are 4 electrons in the outer shell. And actually what's kind of neat about carbon is it can form stable bonds, stable single and double bonds with lots of other elements, but also with itself. So you get these things which are kind of called allotropes of carbon. You get these different forms of carbon which are only carbon-based. We've got diamond here, we've got graphite, we've got graphene, we've got fullerenes, we've got carbon nanotubes. They all contain only carbon, but joined up in all of these different ways, and they all have remarkably different properties. And that's rare for an element. Actually, the person who defined this and described this was a phenomenal woman called Millie Dresselhaus. I don't know if anyone here has heard of Millie Dresselhaus. We call her the carbon queen. She was a Polish immigrant into the Bronx and kind of worked really hard to be able to get to university. She actually was majestic at violin and managed to get a music scholarship to get into a school that would get her into university so that she could pursue this passion she had for physics and engineering. She went on to be kind of the highest esteemed, most prestigious colleague at MIT. She was the first woman to be an institute professor, the first woman to win the Kavli Prize for Science and Engineering. But she also predicted lots of the materials properties of these carbon allotropes. So she predicted what graphene would be like. She predicted what fullerenes would be like. And she gave the world this new way of thinking about how you could engineer materials just from carbon to have these different functional properties to apply to these different technologies. And so Millie Dresselhaus is a fantastic one to look up afterwards, not only because of the science she gave us, but also because of that kind of gritty determination from early on that she wanted to do this. Actually, still, I meet professors today who also play violin, who were trained by people who played with Millie Dresselhaus. You have this kind of effect where scientists who pursued arts and music kind of group together. It's quite beautiful. And one of these carbon allotropes, or one of these particular ways that carbons can join up, is when you have this single-double bond form. So when this is the molecule called benzene. You actually heard a little bit about that. It's particularly exciting this year at the Royal Institution because it's 200 years since Faraday first isolated benzene. So he isolated this molecule. I think it's still in the collection, the amount that he managed to isolate. But this alternating single-double bond structure of benzene gives this molecule really, really interesting properties, and it's actually a feature of lots of the systems that I've worked with. So alternating single-double bonds are really interesting, and I'll get to why that's interesting in a minute. The structure of benzene really perplexed chemists for a long time. I think I learned a little bit about this at school, but didn't realize quite how exciting it was that you had this prediction that the molecule contained these carbon atoms in this 6-membered ring. And now we draw it like a hexagon, and it's quite easy for us to imagine, oh, the hexagon's just flat. But for chemists at the time, they couldn't predict this at all. They had no idea the way that the carbons were joined up in that. It was actually a remarkable woman called Kathleen Lonsdale who managed to decipher this crystal structure. She was born in Ireland and came to the UK actually when she was quite young. But she performed a technique called X-ray diffraction. So she fired X-rays at crystals that she grew of this benzene. And she got these patterns of the X-rays back that had bounced off particular atoms within these crystals and produced these different patterns that she could then kind of back calculate to work out exactly the way the atoms were arranged in that crystal. So X-ray diffraction is really powerful because the wavelength of X-rays, this will look funny on the live stream, doing a little wavelength, but the wavelength of X-rays is similar to the spacing between atoms in a crystal. So when you fire those X-rays at the crystal, you get this pattern back that tells you exactly how those atoms were arranged. And Kathleen Lonsdale did this. She built this really beautiful structure and kind of gave the world this incredibly useful molecule. We now knew the structure of benzene and then could take that and think about using that in lots of different chemical structures we went on to synthesize. Her story is actually also incredible. So Kathleen Lonsdale had her PhD exam at UCL, so not too far from here, and her examiner was William Bragg, of the Nobel laureate, who was the first one to demonstrate X-ray diffraction. Bragg actually won the Nobel Prize with his son. They were the first father-son pair to win the Nobel Prize. But anyway, Bragg gave a series of lectures on X-ray diffraction here at the Royal Institution. He gave the Christmas lectures at the RI. So this is kind of cool, right? Kathleen Lonsdale did her PhD, had her exam at UCL, came here eventually to work at the Royal Institution with Bragg. So in the labs downstairs, they developed much of these ideas about X-ray diffraction. Actually, it was Bragg's Christmas lectures on X-ray diffraction that inspired Dorothy Hodgkin to start working on X-ray diffraction. So Dorothy Hodgkin was kind of a teenager, or maybe just a bit younger than a teenager. I think maybe she was kind of 10 or 11 and started reading the books that came out of Bragg's Christmas lectures from this very room, and got so excited about X-ray diffraction, she started doing it. She then became the first and probably only British woman to win a Nobel Prize in science for her discoveries of the structures of penicillin and insulin. So this was all from that kind of excitement about crystallography, Kathleen Lonsdale meeting Bragg, Bragg doing these sensational Christmas lectures, inspiring Dorothy Hodgkin. This is actually a painting of Dorothy Hodgkin that's in the National Gallery. It's quite beautiful. If you haven't seen it, you see this kind of ferocious movement in her hands, and that's because of how quickly she was working to understand these crystal structures. I'm not sure if anyone, I'm sure people in here have heard of Dorothy Hodgkin before. Hadn't heard of Millie Dresselhaus, but have heard of Dorothy Hodgkin. And when she won the Nobel Prize for Science, it was pretty massive, you know. It's not every day that a British scientist wins the Nobel Prize for Science. This was the headline in the newspaper. Can you imagine? Whenever I'm talking to school kids, I show it to them and they're like, and then you have to tell them what science was like at the time. But anyway, so benzene has this really interesting alternating single double bond structure. And what's cool about that, if you remember anything from A-level chemistry, is that means that the electrons don't just sit in those, on those carbon atoms. They're not in these kind of figure of 8 orbitals in those carbon atoms. They spread out and form this delocalized ring. And that delocalized ring turns this system from being a plastic, an insulator, into being a semiconductor. And if you remember anything about physics, you'll remember that materials have energy levels, and these energy levels can be kind of bonding energy levels or anti-bonding energy levels, or we can have this valence band that's our outermost system of where these electrons are, and then our conduction band. And in a metal, the conduction band and the valence band are kind of on top of each other, so metals conduct electricity because there's no gap between the kind of valence band and the conduction band. In an insulator, there's a really big gap between the conduction band and the valence band, so it's impossible for electrons to jump up. So insulators, like most plastics, don't conduct electricity. Semiconductors are kind of this sweet spot in between, which can conduct, because you can either promote electrons up to that excited state or up to that conduction band. In this process, the system would absorb light, or you can get electrons into the ground state, moving down into that valence band, and then they'd emit light. And this kind of process in semiconductors is how we have things like transistors that underpin all computer chips. It's how we have LEDs. It's how we have solar panels. And what's really neat about these carbon-based systems is you wouldn't expect they have that kind of semiconducting property, but they do. So when you have this delocalized ring of electrons, it turns this system from being an insulator into a semiconductor. So we have the electronic properties of something like silicon, which is a semiconductor you've hopefully all heard of, and the processing properties of polymers, of plastics. And that gives you a whole new range of things you can do with technologies. This whole field was actually discovered in kind of the 90s, in the early 90s, by a bunch of scientists in the UK. And I'm not going to expect you to read this. This is the abstract of a Nature journal paper where they first published this, but it says light-emitting diodes based on conjugated polymers. So this is LEDs that you all have in your mobile phones and televisions, based on these plasticky materials. And you can say, oh, that looks really old-fashioned. I'm sure that went nowhere. But actually, they sold this company for about £300 million. That was pretty big money at the time. The OLED industry is now worth about $45 billion a year. So it's definitely one we should have tried to keep in the UK. But anyway, what went from seeing this luminescence, so suddenly these plasticky materials could emit light. So you could take thin films of these plastics, and you can actually print them, take thin films of these plastics, inject charges, and then they'd emit light. This luminescence was really, really exciting to see in something that you wouldn't expect to be a semiconductor at all. Now we can synthesize them. We can synthesize them in lots of different structures. We call them kind of small molecules or polymers, depending on how big those structures are, depending on how many atoms there are within that. I've shown you a few small molecules here, particularly this helicene structure we'll come back to later on. So that's this molecule that has 6 of these benzene rings connected together. Polymers are long chains of those carbon atoms joined up. And you can kind of repeat them lots and lots of times. But what's neat about these materials is we can control their optical and their electronic properties through their chemistry. So if you want to make them emit a different color or absorb a different color of light, you do that with chemistry rather than trying to put filters in front of white lights. And that's actually why OLED displays have such incredible colors or such fantastic contrast, or they can be much lighter or more lightweight than their kind of inorganic counterparts. They can be low cost. We can print them onto flexible surfaces. So whereas you couldn't before with inorganic semiconductors print onto something that was like a plastic, if you're taking a plastic that you can process at low temperatures, you can actually print it onto these flexible surfaces. They can be biocompatible, so they're carbon-based, so you can start to do really clever things with device design, because your semiconductor is now made of similar things to the types of systems you might want it to interact with in your body. They can transport electrons and ions. Electrons, great for electronics. Ions, great for biological systems. You can miniaturize them, so you can create technologies that are kind of the size of an individual molecule, which is tricky if you're trying to find where they are on a surface. But actually, it means you can do really, really clever things when you want to try and kind of optically address them or read them out. And you can scale them. One thing that's really beautiful about molecules, particularly for something like quantum technologies, is often if you imagine something like, say you wanted to make a quantum computer out of superconductors, you have to find a way of producing all of these qubits so that every single time those superconductors behave the same as every other time you've made them. If you synthesize molecules, every time you do your synthesis, all of the molecules are the same because organic chemistry is kind of completely scalable. You can get infinite replicas that are identical to each other. So they're a really beautiful platform for thinking about creating new technologies from. And they've been used in lots and lots of different ways. They underpin all of the OLED display sector. Actually, when I started my PhD, we were promised we'd have flexible televisions by the end of it. We didn't quite get there. This LG 65-inch fully rollable display came out in 2023, and it went off the market incredibly quickly. I don't think anyone actually wanted a fully rollable display. It seems completely unnecessary. But these kind of conformable displays are things that people might want for kind of consumer electronics. So you don't want something you can fully roll up. But you do want them, even for kind of artworks. It's quite cool that you can print these kinds of things onto flexible surfaces. They've done a lot for photovoltaics, so both for kind of organic photovoltaics and hybrid, laying these molecules on top of silicon or other inorganic semiconductors to boost the efficiency and make use of kind of interesting quantum phenomena to access different wavelengths of light and things like that. So in OLEDs, in the display sector, they've been brilliant. In photovoltaics, they've done a lot. In clever things, like these kind of smart windows, these are windows that are engineered to be transparent to visible light, so you can let visible light through. You can see out of your window, which is pretty good, because that's what you want to do with a window, but they absorb in the ultraviolet and the infrared, so you can generate electricity and then moderate heat into a room through that. There's quite a lot of applying these systems to kind of health monitoring, and then also in diagnostics and therapeutics. So carbon-based semiconductors have both transformed existing technology sectors, but also opened the door to new technologies. And I think the kind of innovation continues to happen and continues to be this kind of beautiful intersection between chemistry, physics, and engineering that gives you this kind of adventures in material science. So the part that I particularly work on is thinking about this aspect of these beautiful molecules called chirality. Hopefully some of you have heard the word chiral before. Chiral objects exist as a pair of non-superimposable mirror images, like your left and your right hand. So that's a kind of fancy way of saying if you put your hands together palm to palm, they're mirror images of each other. But if you put one on top of the other, no matter how much you rotate your top hand, it's not a mirror image of your bottom hand. And actually, we see chirality across a whole bunch of different length scales. So we see it in subatomic things, in things like electrons and also photons. You might remember from physics or from chemistry, drawing electrons with these little up and down arrows. That's us trying to communicate the spin of those electrons, but the kind of handedness of those electrons. We see chirality in light. This is kind of hard to get our heads around because we can't tell whether light is left or right-handed with our eyes. Luckily, these little 3D cinema glasses can tell, so I'll show you in a moment something beautiful you can see with circularly polarized light. But the kind of way to think about this, and these little GIFs try and show you that, but actually the electric field vector of the light traces out a spiral as it moves towards you. So circularly polarized light is just that propagation of light towards you, tracing out a corkscrew or a corkscrew shape, clockwise or anti-clockwise as it moves towards you. And actually, we try and harness this in the science that I work on. We see chirality in molecules. These are the molecules I've already shown a lot of to you, but these are these helicene molecules. And you can see it here better than in the chemical structures I showed you before. But actually, these molecules can't sit flat on a plane. They trace out this little spring-like structure, so they coil clockwise or anti-clockwise, depending on the chirality of the molecule. You can actually keep adding benzene rings. That depends on how good your chemists are. And you can keep going. You can make these spirals kind of longer and longer. And so if you look at them from the side, you get this beautiful coil structure. So you get these left and right-handed molecules. And actually, that's common in lots of biology. So DNA is all right, or all naturally occurring DNA is all right-handed, all proteins are left-handed. But chirality is a design rule we see a lot in biological systems. And obviously, the crystal structure of DNA was proven to be in this helix. We see chirality at really big length scales. So you can see chirality in shells. We see it in fusilli pasta. I know that's human-made. That's not a naturally occurring thing. And we see chirality in the barks of lots of plants. So if you look closely at the barks of plants, they'll often twist in one direction. And we see chirality in these beetle shells, and I'll show you momentarily how beautiful that can be. And then we see chirality actually in the arms of distant galaxies, and also in the gravitational waves that come back to us from distant galaxies. So chirality is this really, really interesting design rule we see a lot around the world. It's kind of interesting, the history of the discovery of chirality. It was kind of 10 years after Thomas Young defined or demonstrated that light was a wave, here again at the Royal Institution. A scientist called Jean-Baptiste Biot, a French physicist, did an experiment of optical rotation. So in this experiment, he passed some plain polarized light that was wiggling only in one direction, through a chiral substance. He took two. He took camphor and glucose, so camphor and sugar. And actually, these molecules occur as only one-handedness naturally, so the right-handed form is the naturally occurring one. And he studied the light that passed through these systems and saw this property called optical rotation. I might try and show it to you here with this beautiful light box, which is another feat of majestic art, and these polarizers. So these are just some linear polarizers. I will not try and ruin the demo that we have set up there. So I'm just going to take this slightly less attractive polarizer. And I'm putting this polarizer just in front of the light. So the light is white light. This linear polarizer turns it into light that only oscillates in one plane. This is cellulose. Cellulose is chiral. This is actually just some sellotape, so plant-based sellotape, everyone. And you can see if you look at it through normal light, it's pretty unimpressive. It's just transparent sellotape. If I put that in front of my linear polarizer, and then I take one more linear polarizer and put it in top, you see these really, really beautiful colors. Hopefully people in the room can see, and maybe even people online as well. But you see these really beautiful colors, and actually what you're seeing here is that optical rotation, where every single wavelength of light is rotating by a slightly different amount, so you get these really, really beautiful colors out. And this is just from something completely naturally occurring of this cellulose-based tape. So Jean-Baptiste Biot saw this in this camphor and glucose and couldn't explain what was going on, but had certainly seen something quite beautiful and quite interesting. Fresnel went on to predict that the structure of quartz was chiral. This was proven to be true about 150 years later, but no one had come up with X-ray diffraction yet, so Bragg hadn't come along. But this kind of early ideas that chirality was going to be interesting. But it was actually Louis Pasteur, who was born in 1822, but in the 1840s, Louis Pasteur was attending art school. How cool is that? So long before he gave us pasteurization or vaccines, Pasteur was into a particular type of artwork called lithography, where you kind of etch away an image and then press down something on top and create the mirror image form of it. So he was training in this particular type of art and creating these really, really beautiful images. He was also drinking a lot of wine. He was a French scientist, and he looked at the crystals that formed inside these wine barrels. And this was about 6 months out of his PhD, so that could explain why he was drinking so much wine. But he looked at these crystals, and these were crystals of something called tartaric acid. And he looked at how light, plain polarized light, was interacting with these crystals. And he saw that the light was coming out in these rotated ways. He had these beautiful crystals that were demonstrating this optical rotation. Pastor's a fantastic scientist. If you read his kind of diaries and books, he writes really beautiful things whenever he discovers something. But I think this is a great one. I've made a great discovery. I'm so happy that I'm shaking and I'm unable to set my eyes against my polarimeter. This is a little bit of a polarimeter that we've built over here. But he was so excited by seeing this phenomenon that he couldn't stop himself. I think we could actually show. Should we try and show it, Andreas? Do you want to come and try and help me if I might need help? If we might switch the visualizer. These are some really cool crystals of sodium chlorate that crystallizes in a chiral way. I don't know if I actually need assistance. I think I could have probably done that. Let's try and switch to the visualizer if we can. Is that going to come on the screen? Okay, great. Here, we've just put one of these linear polarizers on top of the light, and then we've got some crystals of this sodium chlorate. And then I'm going to put this on top, and you can kind of start to see this optical rotation in the crystals. It's hard to know how to rotate it. But you can see these really, really beautiful crystal structures and colors. So these are the kind of patterns that Pastor would see when he went on to play around with this tartaric acid. I think that's all good for now. Thanks so much. I've shown you the cellulose. A kind of interesting thing about chirality is how ubiquitous it is in biology. I've told you about DNA and proteins being chiral. Actually, lots and lots of the lock and key mechanisms that underpin lots of biological interactions are chiral as well. So if you're designing fragrances, the receptors in our nose are chiral, so molecules smell very differently if you've got the left or right-handed form. This is a molecule called carvone. One-handedness of it smells like spearmint, the other-handedness of it smells like caraway, and they're quite distinct scents, if you can imagine them. One's kind of chewing gum, and one is something definitely from a spice cupboard. Also in drug design, you have to think about chirality a lot. So when you're thinking about how you design new therapeutics, this is a molecule that you'll know as an over-the-counter decongestant, but the other-handedness of it is methamphetamine, and they're exactly the same molecule, but one-handedness has quite a potent activity, and the other is quite good if you're feeling unwell. Twisted light is super, super interesting. As I mentioned, it's quite hard for us to get our heads around, but actually we can see it. We can see it in the structure of these beautiful beetles. So perhaps if I can go back to the visualizer now. These beetles have a structure, and I'm going to move away from the bright lights, put my beetle there. These beetles have a structure in their shell which is chiral, so every single layer of the material in this shell is twisted a little bit with respect to the layer below. As I mentioned, our eyes can't differentiate that, but these 3D cinema glasses can. So if I put the 3D cinema, you can kind of see that the beetle's got this really beautiful green color. So it's kind of got this almost iridescent green color. And if I put the 3D cinema glasses in front of the beetle, through this lens, you can still see that beautiful color. So that lens is letting through the color of the beetle's shell. But this lens, which lets through the other-handedness of light, lets through absolutely no color at all. So what's happening in this beetle is that chiral nanostructure is reflecting chiral light, and then only one of these lenses lets that light through, and the other lens only lets the other-handedness through, which isn't reflecting at all. So nature has this really beautiful control of chirality. Maybe I can go back, thank you so much. And we can see that. So these jewel beetle shells reflect that twisted light, and actually I can't show you because it's too complicated to set up with this little visualizer, but I can show you at the end because I've got a mirror. If you reflect this twisted light in a mirror, the handedness inverts. This is a weird aspect of physics that we have to think about in technologies a lot. So if the light's green when it comes through one, when you see it in the mirror, it's black and vice versa. And I'll show you in a moment why that's important. Actually, nature has lots of these weird chiral creatures. Mantis shrimps, which are super cool for a lot of reasons, but they exist in very, very deep oceans. And they've engineered their eyes to be able to try and detect as much as light as possible. They actually have about 12 to 16 kinds of photoreceptors, whereas we only have 3. We can only detect red, green, and blue lights. Mantis shrimps can detect between 12 and 16 different colors of light. But they also can detect circularly polarized light. So the rods and cones in mantis shrimp's eyes can detect chirality in light. They have these kind of cool patterns on their shells to reflect it. So biology and nature have chosen chirality as these really useful tools. And kind of what we're thinking about is this useful in technology? And the short part is yes, it's very useful in technology. It's useful in technology because we can control spin, so we can control the spin of light and we can control the spin of electrons. And that's exactly what we do in my group. So those molecules I showed you before, these beautiful helicenes, actually if we look at the electrons in those helicenes, where those electrons sit, like those delocalized clouds I showed you above and below benzene, those electrons actually sit in these spiral structures. So we've got spiral structures where the electrons are, and that means when these systems absorb and emit light, the light that comes out of them is twisted. So you have chiral light coming from these molecules. Also, we've shown recently, and kind of there's big excitement around the world, that if you transport charges through these systems, so at room temperature, if you push electrons through these systems, depending on the handedness of the molecule, you'll get spin up or spin down electrons out. And this is really interesting because usually you only see this spin polarization in systems that are inorganic or things that have big magnets nearby, but very rarely do you see it in a carbon-based material. There's also some kind of neat work showing if you assemble these molecules on top of magnets, you can induce magnetization on those surfaces. And we're really interested in how we can use that. So how can we use this ability to absorb and emit twisted light to create different kinds of technologies? Could we use that spin polarized control to control different aspects of charge transport? And can we use these interactions with light to try and detect fields? This is some work we've been thinking about recently, is can we use these light matter interactions? So if we put thin films of these molecules, can we use those light matter interactions to detect fields associated with brain function, actually? And so you can take these kind of beautiful molecular systems and translate them into technologies that can do things that you can never do with other types of materials. I'll tell you why and go through kind of why it's useful for displays, because I think this is probably the most intuitive one. This is an Apple iPhone display. It has a bunch of pixels inside it. The pixels emit blue, green, and red light. If you took a cross-section of those pixels, they look a little bit like a sandwich. This is a much simplified cross-section, but you have a bunch of layers here that are important for injecting charges, so injecting positive and negative charges from your cathode and your anode. They then travel through your device, and in one of those big sections that I've colored red, green, and blue, that's our kind of active layer. And when your charges travel through there, they meet somewhere within that active layer, they do something called recombining, and they emit light, and that's how an OLED works. So we put these transport layers either side to kind of smoothen that process out a little. But what would happen if you didn't have this clever anti-glare filter there? So this anti-glare filter that you see in that stack near the transparent substrate at the bottom, that anti-glare filter, unsurprisingly, acts to minimize glare. And that's a comment I made earlier, that you want to be able to use your technology outside on a sunny day without light from behind your light from behind you interacting with what image you're looking at on your screen. So if you imagine that electrode at the back is shiny, and you wanted to send a text message, and you went outside, and the sun came from behind you and interacted with that electrode and came back, that glare would distort what you were trying to look at. But you don't have to worry about that because we have these anti-glare filters, and the way they work is they take unpolarized light, they turn it into twisted light, they turn it into this chiral light, that then moves through this sandwich of your display, hits off that electrode at the back, like I showed you with the Beatles before. If clockwise light hits a shiny surface, it becomes anti-clockwise light. That then tries to move down and get out of that sandwich, but it gets stuck at that anti-glare filter. So you minimize glare by trapping that light in the display. So that's pretty brilliant, but it means that if your pixels, your LED pixels, are emitting light that isn't chiral, half of that is getting stuck in that anti-glare filter. So even though you're pumping out all of this light and your poor mobile phone battery is going down very quickly, you're losing about half of that light intensity. So we started working on this because we thought it would be kind of neat if we could just boost that light intensity by making all of those pixels emit twisted lights. And it turns out you can, and you can do really clever things with twisted light as well, in kind of bioimaging or preparing and reading out quantum states or thinking about three-dimensional imaging and things like that. So there are lots and lots of different applications. We can make molecules chiral in lots of different ways, again, depending on the chemist that you work with or depending on the structures that you want to create, and I won't go through those, but again, I'm really happy to talk about these if people have any questions. There are lots of different ways you can introduce chirality into molecules. Something that's really fascinated me about working in this space is about how tiny changes in chemical structure can completely impact how the molecules assemble in the solid state. So if you take these molecules like these helicenes, just inserting a nitrogen at a slightly different position will transform you from something that packs in these really, really beautiful ordered columns to something that packs in this kind of horrible Pac-Man-like structure. And that has huge impact on the electronic and the optical properties. So just playing around with really subtle changes like that massively influences the performance of your device. And we can introduce chirality in polymeric systems and also into different kinds of structures like that. And what's kind of interesting about chirality is it doesn't only exist in organic molecules, but we can also bring it into lots of different kinds of structures. Actually, these sodium chlorate crystals that I showed you over here that did that kind of neat optical rotation, they're a fascinating example of something which isn't itself chiral. It's not chiral on its own, but when you crystallize it, it becomes chiral. So even though about only 10% of non-biological molecules are chiral, if you look at all crystals, 23% of them crystallize in a chiral way. So there's some tendency that things want to assemble into a chiral structure, and probably for useful optical properties or some kind of more efficient charge transport. There's been lots of looking at this. You can introduce chirality into perovskites, you can do it into nanowires, you can have organic frameworks, metal organic frameworks, and covalent organic frameworks that are chiral in metasurfaces and topological systems. We can have a lot of fun with trying to make chirality in materials. And that's kind of what we've focused on in our group. We've introduced chirality across lots and lots of different length scales to try and control those light-matter interactions and then also boost them. What we started to explore was actually how the origins of this chiral response depended a lot on the size of the system you were looking at. So if you were in these isolated molecules, you relied a lot on how charges were moving in your system, how your electron dipole and magnetic transition dipole moments were aligned. Whereas when you start to build these up into these structures, a bit like our beetle shells, you depend a lot more on the thickness of your structure or the refractive index of your material. Actually you can start to do this if you imagine going back to those polymers that I showed you before. You can assemble and introduce chirality across multiple different length scales. And this is the kind of thing we work on, is how can we coerce these systems into becoming the most strongly chiral light matter interacting system that they can be. And you can do this at kind of this individual polymer chain level. You can thread them together and make these kind of bundles of chiral nanofibers. You can thread those nanofibers together and make something with chirality on a different length scale, and then build it up until you get to kind of micron scale systems. And there you have opportunities at every level to amplify that chiral light matter interaction even more, so that when you go to translating it into some kind of technology, you have the strongest twisted light possible. And that's kind of neat when you want to build tech out of these systems. So we've done this in lots of different ways, and I won't go through this unless people want to ask questions about it, but we've played a lot around with what the molecular design looks like. We've done some really neat work trying to pattern this on really small scales, so showing that actually we can print really ordered chiral domains of these systems, and we can put molecules inside different molecular structures and boost the chiral light that comes out. And that's kind of some neat work that we did quite recently. And also we can control the way that these molecules assemble. So we can either get these columns standing upright on a surface or lying flat on a surface, which has really profound impacts for how they interact with light or interact with electricity. And so we're really, really interested in different ways that we can do this. And then the different ways that we apply this to technologies, we're thinking about different cool structures that we can use to do this in OLEDs and also photodetectors. This is kind of interesting. Sorry, I've done a rogue thing here. This is kind of interesting if you want to make better displays, so more efficient displays. But also if you want to try and multiplex in optical information processing, and that means that sending information down something like a fiber optic cable, you can make use of both the clockwise and anti-clockwise channel to send that. So you kind of double your data transmission rates if you use these chiral detectors. And we've shown that you can do this really cool control of spin polarized transport, and this is a really, really exciting area of science that maybe, if you're inspired, you can go and read about. But in conductors, it's been known for a while, if you have a chiral conductor, that the resistance depends on the relative direction of the magnetic field and the current. If you've got a left or a right-handed system, you'll change your resistance. And this is a property called electric magnetochiral anisotropy. And this is kind of super cool, but only in conducting systems. Whereas in these semiconducting systems, as I mentioned earlier, you get this really interesting spin-polarized electron transport through a system of a single-handedness that actually has massively versatile applications in different technology areas. And then, as I mentioned, actually way back at the start, you get these kind of interesting magneto-optic effects. This is a property called Faraday rotation. So much like the optical rotation that I showed you here, if you have your chiral system in a magnetic field, you have a measure of this optical rotation that depends on the strength of your magnetic field and also a property called the Vade constant that depends on your material. So if you know a lot about your material and you can measure your optical rotation, you can then work out how strong that magnetic field is. So you can sense magnetic fields using light. And this is really, really powerful, actually, because you can start to think about doing this magnetometry with low power, but to be able to detect magnetic fields associated with brain function, or actually a way they use it a lot is to look for defects in aeroplane wings. So you can do kind of non-destructive defect inspection by using these magneto-optic approaches. And this is also neat to talk about here because Faraday actually demonstrated this Faraday rotation with this apparatus that's downstairs in the museum here at the Royal Institution. But he first saw this kind of interaction between light and magnetism, doing these kind of optical rotation measurements through these crystals. And while we say that very easily now, because you know about the electromagnetic spectrum, or you know about this interaction between electricity and magnetism, at the time Faraday was around, absolutely no one had united these two fields yet. It was kind of mind-blowing, this interaction. We were just learning about electricity and magnetism. And then suddenly this interaction with light started to manifest. So just scientifically, it's such a phenomenal concept. This was what he said: "I've at last succeeded in magnetizing a ray of light." Just completely beautiful. So kind of what next? What are we trying to think about doing with these systems? Well, if we can use this spin control from these chiral molecules, we can think about building new types of LEDs or different types of memories. If we can get molecules that are single photon emitters, so emit single twisted photons, and we could couple them into crystals, we could use those for kind of photonic quantum computing. And what's really exciting, actually, is that everything I talk about is really exciting, but another really exciting thing is there are lots of energy levels within these systems, and to make a quantum technology, you need to be able to create superpositions between these different quantum states. So if you could engineer these molecules such that you could optically create these superpositions and optically read out that quantum state, then you have this very versatile platform for quantum technology that operates at room temperature, that's kind of infinitely scalable and also miniaturizable. So chirality is absolutely fantastic. As Chris mentioned in the introduction, I care a lot about talking about science too. We've tried a lot in our research group to make science accessible to everyone. These are some photos actually from the Exhibition Road Festival that we held at Imperial last weekend. I'll let you work out what these are. Two of them are a kind of visual interpretation of Schrödinger's equation. The purple room is a quantum disco, of which I held 8 over the course of the weekend for primary school kids. And then we had a really beautiful artist interpretation of atom interferometry. But I think there's kind of huge opportunity at that intersection of arts and sciences in translating science into a way that's accessible and exciting for everyone. I always make our lab really cool t-shirts. Here's an evolution of all our cool lab merchandise. If that doesn't convince you to become a scientist, I'm not sure what will. And I'm a massive, massive fan of contributing to Wikipedia. So this is kind of one of my secret passions, is building there. But beyond that, I'll kind of tell you 2 other things that I've been working on recently that I think are kind of fun. I've written two children's books, 2 children's picture books about science. One is called Nano, the Spectacular Science of the Very, Very Small, and the other is called Light, the Extraordinary Energy that Illuminates Our Universe. And they both explore these kind of different parts of the science that I work on, which I think isn't actually explored very well in children's books. Usually it's about space or the human body. You don't get these cool parts of materials or different kinds of technologies. At the other extreme, I'm really, really keen that we communicate science more effectively to policymakers. So actually, just yesterday, I finished a course that I've been running for 8 weeks for civil servants on quantum technologies. So taking a bunch of civil servants into Imperial every Friday morning and trying to teach them quantum technology. But it's been absolutely brilliant. You know, I think we have such strength in our government of enthusiasm about science and technology. And when we advertised this course, we had applications from across different government departments, you know, Department for Transport, Department for Energy and Net Zero, MOD, all of these different places who are really excited about the future of tech. And this has really shown me that, the future's very bright. We're going to have so many opportunities for the types of science and engineering that you might be excited about in this audience, because the government are enthusiastic and they see the potential of AI, of engineering biology, of semiconductors, of quantum technologies in benefiting the UK. So yeah, I care a lot about how we communicate science. So I'll end just by saying chirality is massively, fantastically wonderful. Why should you care about it? Well, nature's obviously chosen it as this kind of design rule for biological systems and for the natural world. And hopefully I've shown you that has this huge potential for different kinds of technologies as well, both in controlling light and electron spin. So that's all from me, and I'll answer any questions, so thank you so much.